It's our pleasure to have with us Dr. Wang. Okay, Dr. Wang is quite accomplished as a scientist and inventor, and it's really very good for us to have him here. He just recently moved from Oregon State University to Baylor University, where he is an endowed professor there in the engineering school. So that means high distinct honor to be an endowed professor. He got his bachelor's degree from, here it is, the MIT of China, and hopefully I pronounced it right here, Qingzhou University. He got his master's degree in China as well at the Institute of Semiconductors, the Chinese Academy of Sciences, and he's got a PhD here in Texas, right, at the University of Texas at Austin. And he spent time in industry, teaching at Oregon State University, and now he's at Baylor. And he is looking for new students to work in his lab, earning their advanced degrees in electronics and engineering. And that's why he comes to Eternal, because, hey, this is the place to get really smart, good, wonderful students. Yes? So let's thank Dr. Wang for coming and give him a warm welcome.
Thanks, Gary, for the nice introduction. It's my great honor to be here at an Eternal University to share my research and also, my experience from a PhD to my academic career, and also the openings of the research opportunities in my group. So today I'm going to talk about the heterogeneously integrated nanophotonic materials and devices from fundamental science to emerging applications. So as Gary mentioned, I just moved from Oregon State University to Baylor University in August 2022, and I'm currently establishing my lab at BRIC. So this is the building at Baylor to support the engineering research. And my lab, so we are building up the new lab. You can see this is the state-of-the-art testing of the electronic testing facility with the biosensor development and biomaterial synthesis. And currently I have a postdoc and 4 PhD students. I'm looking for more students in fall 2023, so I will explain more about these positions later on in my talk. All right, so to start my research, I want to give a little bit introduction to the background of my work in nanophotonic materials. So for the engineering student in electrical engineering, you're probably familiar with semiconductor material. For semiconductor material, the periodical arrangement of the atom will induce the band gap for electrons. And similarly, if we have this periodical dielectric structure with wavelengths comparable to the optical wave, and you can generate a photonic band gap, which means at a certain wavelength, the light can be reflected. One of the examples is that nature created a microbiology called diatom. So you can see many different vivid colors and optical microscope. The color actually doesn't come from the chemical agent. It's actually coming from the periodical air holes embedded in the shell of the microbiology. So this clearly tells you can get some photonic crystal from nature. And the other type of nanomaterial I want to introduce is called the surface plasmonics. And it's actually quite simple. For metals, you have a lot of free electrons. And under an external high-frequency electromagnetic wave, like a light wave, that light wave can force the oscillation of the electron and induce the accumulation or depletion of the electron at the surface of the metal. We call that surface plasma. And that one can induce a high intensity electrical field at the surface of the metal. For example, this is a gold nanoparticle. And under a laser focusing, you can see strong light scattering. And again, this is not new. So this is an example of a surface plasmonic, which is called the Cuck's cup. It's a wine cup used by the Roman Empire in the 4th century. And you can see this in the British Museum. This Cuck's cup, you can see a ruby color if you shine light from outside. But if you put light source inside, from jade color from outside, if you put light source inside, you can see the ruby red color. The reason is because they are tiny gold nanoparticles doped into the glass material, and you can demonstrate surface plasmonic scattering at the different light source. Quite neat, quite neat. Okay, so what's my research? So my research focused on the core material by combining photonic crystals with plasmonic. And in the meanwhile, we integrate a broad spectrum of other functional material to make the device to meet a different kind of engineering applications. For example, we created this one-dimensional photonic crystal on silicon material, and then we integrate other material like a transparent conductive oxide. So we can build an optical modulator, which means you can use the electronic signal to control the optical signal, which I will explain later. And also, we can integrate with other material, for example, called metal organic framework. This is the porous material which you integrate with the plasmonic, and you can absorb the vapor in the environment, and you can develop very ultra-sensitive vapor sensors. And also, as I mentioned, we use a diatom as a nature-created photonic crystal. You can see there's a periodic air hole at the surface of diatom frustum. And using this nanostructure, we can build ultra-sensitive biosensors for healthcare, for drug detection, for law enforcement, for a different spectrum of applications. And of course, I didn't get all this achievement alone. I have broad collaboration with many faculties or the industrial researchers. And so this is just some of them. And the application. So the first application is the optical communication, especially for high-speed, energy-efficient data centers and for on-chip optical interconnect for artificial intelligence, for high-performance computers, and for optical sensing. It's primarily focused on healthcare. We can develop ultra-sensitive sensors for cardiovascular biomarker, for cancer biomarker, and also for public health and environmental protection. And in the process of doing that, so in the last 15 years in my professional career, I raised about $9 million of federal and industrial grant and published more than 100 publications, including 7 issued patents. And these are the funding resource, which has supported my research in the past years. Okay, so that's a brief introduction. My topic today will focus on the 2 of the most important applications. The first one is the transparent conductive oxide for photonic integrated circuit. Especially I will focus on nanocavity modulator and the microring modulators. And this is important for future data centers, for energy efficient data centers. I will spend one slide to introduce the necessary background of optical communication. We know we use information, all the high tech every day, and we send and receive an enormous amount of information every day. So one simple way to send and receive the information is wireless, but that one doesn't provide you enough bandwidth. If you're considering the whole IT infrastructure as a transportation system, wireless or electrical interconnect, they are basically like a local street. Most of the high bandwidth data is actually transported through optical fiber. This is the optical network. It's just like a freeway and a highway of the transportation system. So those are the backbone of the communication system. So the idea is very simple because this is optical fiber, which is highly transparent to light. So if you couple the light into the center of the fiber, which is called the core, it has a higher index than the cladding material. So light can be confined in the core due to total internal reflection. This is a very simple mechanism you have studied in high school physics. And then, because the material is highly transparent to optical light, and then there is almost no loss in the fiber. So you can send high-speed information over an optical fiber for hundreds of miles with almost lossless. And this one is actually optical fiber network has already linked all the world together, like internet, telephone network, cellular network, cable TV, and Internet of Things and data centers. So using the fiber is not new, has been going on for centuries. But is there any way you can build a different type of optical waveguide? So basically you use a planar circuit technology. Instead of using this cylindrical fiber, which can only be fabricated by drawing glass, you can actually using a nanofabrication to create this kind of rectangular waveguide. And this one has a core with a high index and a cladding with a lower index. Based on the same total internal reflection, you will be able to confine the light within the core of the fiber. So the advantage of this structure is you can design way more complex devices, different devices, and put them together, just like an electronic IC. You use a CMOS technology. You can integrate billions of transistors on a single chip. So using a planar light wave technology, we can potentially integrate all different optical devices on the same chip rather than using the optical fiber to link discrete optical components. And this one will greatly provide you the advantage in terms of performance and cost. Well, the idea is not new. In 1969, a scientist called Stuart Miller proposed this idea using a waveguide as a photonic integrated circuit for highly integrated functional unit. But he said there is a conviction that the new miniaturized optical circuit will prove to be useful. But we must wait a while longer to find out how useful this technology can be. And this a little bit of while turned out to be several decades. Only in the 2000, when the telecom bubble started to increase, people have demonstrated this silicon-based planar light wave circuit technology for telecom modules. But now, after 10 years, Intel has commercialized a silicon photonics platform which can put lasers, photodetectors, modulator on a single chip and demonstrate optical transceivers. And this one has already been used in data centers, and there are millions of units shipped every year. Everyone knows Intel is the largest chip company. They make a lot of CPUs, right? But Intel is also the largest photonics company. They ship the largest volume of optical transceivers for data centers. They account for almost 60% of the total market. Okay, but you will ask why we need a photonic integrated circuit. The answer is the bandwidth. So if you look at the GPU, you use it for AI, for training, okay? So like a NVIDIA Tesla V100, it has more than 5,000 cores. And it can do more than 125 teraflops of computation, but it consumes 300 watt of power. And if you're looking at enterprise level of the chip, which integrates 16 of such GPUs, it consumes like 10 kilowatts. And if you look at the IBM Summit's top supercomputers, it consumes like 13 megawatt of power. Where the power goes to, you may think it's used for computation, but for such a highly parallel linked system, computation actually nowadays uses less energy comparing with interconnect. Because you have so many different units, you need to communicate with each other. There are more energies being used to move the information around than doing the computation itself. So if you look at the trend, the power for input and output is actually accounting for more and more of the overall power. So which means electrical interconnect consumes too much power, and we have to use optical interconnect to provide all the bandwidth with acceptable energy consumption. And this is the motivation for the photonic integrated circuit. Okay? And you can see this is the 400G commercial module that is being used nowadays, and this is a long-term vision. So basically you can integrate all this optical component, photonic integrated circuit, with the CMOS circuit, and you can do the single chip integration of electronic and photonics. So that's the ultimate goal in the future. And of course, this photonic integrated circuit can do more than data centers. You can use it for 5G and 6G, and you can use it for remote sensing because you can directly process high bandwidth optical data directly from the camera, and also for the machine learning and AI acceleration. If you need a lot of energy to train the AI model, if you use ChatGPT these days, you probably don't realize how much energy you use. For every request you send to ChatGPT, it will probably consume like half kilowatt hour of electricity. So basically it costs you like 10 cents per request, just the energy itself. By using photonics can greatly reduce the energy consumption. Okay. So as I mentioned, we want to use photonic integrated circuit for data centers, but there is a problem here because the computer uses electronic signal, and optical network can only transmit optical signal. So you must have a device that can convert electronic signal into optical signal, and then you can send it over the fiber. So this is how an optical fiber network works. So you have a laser, you couple it into a modulator, which is the key device here, This modulator takes in the continuous wave laser, but in the meanwhile, you can use electrical signals to drive the modulator. You can think the modulator is a tiny switch. You can turn on and off the light based on your input electronic signal. And then the output from the modulator will be optical pulses that corresponding to the binary or analog signal you applied to the modulator. And then you can couple the light into the optical fiber, send it over a long distance, and the receiver, you have this detector, which can convert it back into electronic. And that's how optical network works. And of course, you can see the key is how you can build this modulator with small size, high energy efficiency. This is one of the examples based on the Magenta interferometer. So you have the input light, you split it into two arms. At one arm, you apply electronic signal, so you change the phase. When they combine, they will form either constructive or destructive interference, and then you can have this modulated optical signal. We want to build everything on silicon because silicon is the most matured platform, and so we want to build an electro-optical modulator also based on silicon. And you have three different mechanisms. The first one is the forward biasing. So basically, we inject the current into silicon, and you can change the refractive index. But the problem is it consumes too much power and it's relatively slow. And the second is based on the reverse p-n junction. So if you have taken semiconductor courses, you know when you form a p-n junction, you form a depletion zone. And if you apply a reverse bias, you can change the width of the depletion zone. And then you can change the refractive index. This type of modulator is very quick. It's very energy efficient. But the problem is the driving voltage is too high. It's not really energy efficient. So the third type is based on a MOS capacitor. Again, you require some semiconductor device physics. So basically, you have an insulator, you have a p-type and an n-type semiconductor. You apply a voltage, so electrons will accumulate in the n-type semiconductor. Holes will accumulate in the p-type, and then you can change the refractive index. For this type of MOS capacitor, it combines both high speed and energy efficiency. And most important, you don't really need to limit your material choice on silicon. For example, you have this silicon waveguide, but the gate material doesn't need to be silicon. You can have different type of material integrate on top of silicon. For example, we can integrate 3,5 compound semiconductor, graphene, or the transparent conductive oxide. So using this heterogeneously integrated material system, you can greatly enhance the electro-optical modulation efficiency. Okay, so some work has been done before. You know, you can put polysilicon 3,5 primary indium gallium arsenide and the transparent conductive oxide and the graphene on top of the silicon. And also you can have different choice of the devices. Due to the time limit, so I'm not going to the details. But I want to emphasize the material here. So we use transparent conductive oxide. So what kind of material it is? If you think of the material you have, it can be either conductive but not transparent, like a metal, right? So it's conductive electricity, but it's not transparent. Or it's transparent but not conductive, like a glass. So they are very rare material that can be both conductive and transparent. So you only have a few choices, like the indium tin oxide. And that material is kind of very unique material that can provide you both high optical transparency and high electroconductivity, and which is preferred for our electro-optical modulator. And this one example is the indium oxide, which shows the crystalline structure and the band diagram of the material. And this material, like the transparent conductive oxide, has been widely used in industry for several decades. One of the examples is the display. Okay, have you ever looked at your cell phone? Your cell phone, so your cell phone screen, so it must be transparent, right? Otherwise you can't see anything. So it's transparent. But in the meanwhile, it must be conductive so that you can apply the signal to the pixels and then change the color or change the brightness. So this material, it has already been used, and you are benefiting from this material for a long, long time. But you probably just didn't realize that. And also for solar cells. So for solar cells, it needs to be transparent to the sunlight, converted it to the electricity, and then that electron can conduct the current out. So that's being used for a long time. But for integrated photonics, this material is still new. So there are unique properties comparing with other materials, semiconductor material. So first is, it's highly conductive. You don't have to dope it. It's automatic dopant. And also, it gives you a very strong electro-absorption, electro-optical modulation effect which I will explain later. So here is how we can use this transparent conductive oxide for electro-optical modulator, as we mentioned before. So this is the design of the structure. You can see this is the silicon waveguide, but we introduced this periodic air hose along the waveguide. So this will basically serve as a Braga mirror, so it will reflect the light. But if you have two symmetrical mirrors, it will form a cavity, resonant cavity with the center. And then you couple the light. So if it's off resonance, the light will be rejected. But if it is on resonance, the light will tunneling through. This is kind of similar to the quantum tunneling effect. So you have an energy barrier, but the particles can potentially go through this energy barrier due to the quantum tunneling effect. This is exactly what happened here. So this photonic crystal serves as a barrier, but this cavity serves as a channel. So photon can tunneling through this photonic crystal waveguide. But this alone cannot be a modulator. We have to put the electrode. So basically we use a transparent conductive oxide as an electrode on top of the cavity. And then we apply a voltage. So you can see electrons will accumulate in the transparent conductive oxide, holes will accumulate in silicon. That one can change the refractive index of the material. If initially the cavity is on resonance, you apply voltage, it will be off resonance because of the refractive index is changed. And then you can control the on and off, or control the transparency of the cavity. So you can build an optical modulator based on this. The advantage is this structure is extremely compact. So if you're comparing with the cavity, the volume of this region is only about 2% of the wavelength cubic, or the length of this structure is only like a half micron. But if you're comparing with a traditional electro-optical modulator, it's probably hundreds of microns. So basically, you greatly reduce the size of the electro-optical modulator. And why you need to do that? If you're considering the energy efficiency of your transistor, make it smaller, it will be more energy efficient. So it's the same way here. And we make this modulator, and this is the transmission. When you apply a voltage, you can shift the transmission, so you can shift on and off the modulator. And this is fabrication. So we need to use very sophisticated tools like electron beam lithography, reactive ion etching to form the waveguide, and then we can dope it to form a contact region, and then we use atomic layer deposition to include this high dielectric constant insulator, and then we use sputtering and liftoff to put on the gate material on top of the waveguide, and then we use metal and to make the metal contact. So this is how the process. It's only show the major steps, but actually this totally requires more than 30 steps of semiconductor device processing. And this is some of our device. You can see this is the SEM picture of the fabricated device, and this is the testing. And you apply voltage, you can change the transmission, and you get the modulation. So I just skip the details here. And then this is the high-speed testing. So you have this electro input signal, and this is the response from optics. And this is the high-speed data you send through the optical modulator. We call this eye diagram. So I just want to skip the details here. And another device I want to briefly touch is called the micro ring resonator. Okay, so it's just like a ring, everyone wave. But this ring is much, much smaller. It's only 10 micron size. So you couple the light, and then you can couple the light into the micro ring, and there's no light is going to be transmitted. But you apply a voltage, you can change the refractive index of the material, then the light can tunnel through this region. So this is similar to nano cavity I just mentioned before, but instead of cavity, you are using the ring to form an optical resonator. And this is a device fabrication, and this is one of the device we fabricated, and this is the optical imaging showing the fabricated device. You can see this is the ring here, and this is the waveguide, and this is the electrode where you can apply the electronic signal, and this is the testing setup, and this is the transmission curve when you apply different voltage. And you may ask why you want to use a micro ring comparing with the nano cavity. The reason is called the bandwidth density. So people have already shown you can use a micro ring to form a commercial modulator, and this is actually from Intel. So Intel has already developed this micro ring resonator modulator, and it's already being used in the commercial product. But the issue is the bandwidth density and the driving voltage is still too high. So that's why my group is currently working with Intel to develop a photonic integrated chip for photonic integrated circuit for on-chip wavelength division multiplexing. Let me explain a little bit. So what is the wavelength division multiplexing, or WDM? So if you have a waveguide, if you couple it into one microring, you are only modulating one particular wavelength. But if you design different microring with a slightly difference in the radius, you can actually induce a resonance at a different wavelengths. So in that case, we can couple multiple wavelengths into a single optical waveguide. And each microring can individually control and modulate the wavelengths. So basically, we are able to put multiple wavelengths into a single microring. And this is called the wavelength division multiplexer. Imagine if one channel can carry 100 gigabits. If you have 8 channels, you can scale up the bandwidth to 800 gigabits. So this will greatly enhance the bandwidth density of your system. And this is what Intel wants us to do on this project. So we have shown that this is possible. So basically, we made a waveguide coupled into 4 different microrings, and each microring can have each individual working wavelengths, and we can apply the voltage to control the working condition of each microring, and we can change each resonant wavelength of the microring individually. So that's the plan. And of course, we are closely working with Intel, so this one shows a 12-inch wafer, 300-millimeter wafer, fabricated by Intel's foundry. So Intel has a foundry in New Mexico which can fabricate those large-size photonic integrated circuits. And our design is coupled with the other professor's design. We call the University Research Center. There are 7 professors in this project. So we have our design grouped into a single wafer. And this is the chip, one of the chip after dicing. You can see there are many, many miniaturized optical circuits in this chip. And this is the zoomed in view of the one of the microring. So you can clearly see the quality of the fabrication. Okay, so I probably use a little bit more time than I expect. So here I want to jump to the next topic is biosensor based on diatom biosilicon. So I introduced the concept of diatom at the beginning. So you may ask, what's the unique property of the diatom material compared with other biosensor materials? The first one is the photonic property. And people have been observing diatom since the invention of optical microscope for almost 300 years, because they can always find the diatom with different colors, because different species give you different colors. They're kind of like a magic, so they are kind of fancy object. This structure can give you very unique photonic structure. For example, people focus a laser into the shell, and you can see there is high order diffraction from across it. And also, sometimes it looks like a lens. You focus a laser, you shine the light, it will be focused by the structure. But in addition to that, this diatom material also offers you a very rich surface chemistry, because the surface has a lot of hydroxyl group. You can easily functionalize the surface, so you can capture the biomolecule you want. And also, it's a highly porous material with large surface to volume ratio, more than 200 meters per square per gram, and you can easily capture the molecule you want. And also, this nano periodic air hose can be used as microfluidic devices. So you'll force the fluid to flow through the channel, and then you can focus the analyte into the region you want. And last but not least, it's abundant and low cost. You don't need to nanofabrication to get this photonic structure. You can directly use diatom culturing to get millions and billions of such material for biosensing. And how we are using this structure for biosensing? So we rely on optical testing. So one method is called the Raman scattering. So what is Raman scattering? So basically, if you are in the chemistry major, you know it quite well, because this is the chemist Raman, who discovered that, and he won the Nobel Prize in 1920s. So basically, you shine the laser onto a molecule, you excite it into a high energy level. Usually, it will return to the initial level, and the scattered photon has the same energy as the laser. This is called the Rayleigh scattering. So it's a elastic scattering. But if the energy of the electron return to a different energy, then the scattered photon can have a different energy. This is the inelastic process. So this Raman scattering is kind of a fingerprint to the human being. Different molecules, they have different chemical bond, and they can give you different Raman scattering spectrum. But the disadvantage is it's very low sensitivity. So this nonlinear process only occurs 1 out of 10 to 8 photons. So its sensitivity is too low. But about 40 years ago, or 45 years ago, two scientists found that if you put the chemicals on a roughened metal surface, you can greatly enhance the Raman signal. Initially, they thought it's due to the enlarged surface area, but later on people discovered it is the surface plasmonic enhancement that increased the Raman sensitivity. The reason is because at the surface of the metal, the electric field is significantly enhanced, and the Raman sensitivity is proportional to the force power of the electric field. And with that enhanced electric field, you can greatly increase the sensitivity of the Raman. We call this surface enhanced Raman scattering. And you can actually detect a single molecule with a good engineered surface search substrate. And indeed, in the last 20 or 30 years, a lot of metallic nanostructure has been developed to enhance the search sensitivity. But my group take a slightly different approach. So we integrate plasmonic nanoparticle on diatom, which is a photonic crystal material. So when you put a metallic nanoparticle on the photonic crystal, the photonic resonance and the plasmonic resonance, they will couple together and induce even stronger optical field enhancement. For example, we show that if we put the nanoparticle on the surface of the diatom or put the nanoparticle inside the pores of the diatom, we can get significantly enhanced electrical field, and that one can induce very strong surge intensity. And this is a simulation to show you this nanoparticle may be greatly enhanced, but due to the time limit, I will skip the details. And here is what we do. So basically, we used a diatom culturing technique. We feed this diatom with some food. It's just a sand, a silicon material, and shine the light, they will grow. And then you can get high density diatom fructose. And unfortunately, we have to kill those little creatures to remove all the organic part and leave the glass shell there. And then we integrate the nanoparticle at the surface. So you can see this is the SEM picture showing the nanoparticle is deposited at the surface of the diatom. And then we show that you can greatly enhance the light scattering due to the presence of the diatom fructose. And then we conducted surge testing. So you can see the blue curve is the surge from a nanoparticle on a flat glass substrate. And the red curve is the surge signal from the diatom. The signal is greatly enhanced. In order to avoid the random effects, so we do a 2D mapping of the surge over the entire region. So this is the imaging, optical imaging of the diatom, and this is the imaging of the surge mapping. So you can see these two are highly correlated to each other. It shows you the enhancement is not random. It's systematically from the diatom fructose. Okay, but how can we use it for more advanced application? One thing for practical application is the interference. For example, if you're considering detecting something from the blood, like a biomarker from blood, it's dauntingly difficult because the blood is not a simple solution with the thing you want. There are so many, white blood cell, red blood cell, platelets. These things can easily bury the signal you want to detect. And also, if you want to detect something from the food, like the toxic hormone from food, it's also very difficult because you have protein, carbohydrate, fats, vitamins, all these things there. And those things can have much stronger signal comparing with the things you are interested in. So how you can do this? If you're a chemist, you know the solution, right? It's chromatography. The idea is very simple. If you cannot detect them together, let's separate them. So you do the chromatography. You basically apply high pressure to force the different molecules to separate as they are diffusing along the chromatography rod. And then you use mass spectrometry to detect the different molecules. And that's how the chemist does. This is very efficient, but it's low. It's very sensitive, but it's pretty expensive. Whether we can develop a more portable, a lab-on-a-chip optical sensor that conduct the same thing, but with much lower cost. So here my group turned into a into an antique technology called the thin layer chromatography. So this is the working principle. For a thin layer chromatography, it's a porous medium. And we can have the element flowing along the porous medium. And if the molecule has weak interaction with the medium, it will be carried by the faster moving element. But if the molecule is polar, has a stronger interaction with the porous medium, it will move slower. And over a certain distance, these polar molecules and the non-polar molecules, they will be separated. And then we can combine this thin layer chromatography with surface enhanced Raman scattering, as I just mentioned. We will be able to detect the chemicals in the complex environment. So here we use a diatomic earth or diatomite as the porous medium. This diatomite is just the fossil of Asian diatom. You can find billions of tons of reserve in many different places. And this is the optical imaging, and this SEM picture showing the particles. You can see each one is like a disc-shaped diatom. And each one can show you very unique optical properties. You can see this is a single diatomic, disc-shaped diatomic frostule. And this is the optical diffraction due to the air hole there. It clearly shows the photonic crystal diffraction effect there. And what we do is we make a thin layer chromatography plate out of the diatomic material, and then we put it into an alloy. And then we can drop the analyte we want, and this alloy will separate them. And then we can drop the nanoparticles for the surface enhanced Raman scattering. And this is a very effective technology. It's serves as analytical chemical tools, and you can use it for food safety, defensive threat reduction, water contamination detection, or the law enforcement. You can detect many different chemicals. It's not a particular biosensor that is designed to work with one particular chemical. This is kind of a universal tool for many different chemical detection. And we'll apply this for different technologies. So one of the examples is to detect cocaine from the human plasma. So we show we can separate the cocaine from the rest component of the plasma and also achieve very high sensitivity down to 10 part per billion level. And this is comparable with GCMS. Okay, so that's pretty much all of my technical part. And now I want to give a summary. So basically from the fundamental science perspective, we work on the transparent conductive oxide material. So it offers you very exclusive advantage due to the high carrier mobility, high conductivity, and epsilon near zero effect. And we're continuing to seek better transparent conductive oxide material for better performance. And the diatom biosilica, so it's a nature-created photonic crystal material, can provide you very high optical field enhancement, rich surface chemistry, and unique microfluidic properties. And the application include optical communication and optical sensing. And currently I have 6 PhD student openings starting in fall 2023 in these 4 different areas. The first area is high-speed, low-voltage silicon modulator, and this is a collaboration with Intel. And the student working in this project can potentially have the internship opportunity with Intel in Santa Clara. And also we are working on electron-tunable metal surface. This is supported by NASA, which I didn't have time to talk details about this filtering project. And also optical biosensors for biological photonic crystal material and the machine learning for biosensing. And this one probably requires more computer science background because the third signal you acquired is very complex. Sometimes there's overlap, so we need to use machine learning, artificial intelligence, convolutional neural network to differentiate those signals. So there's computer science knowledge required. And for the interested candidate, you can directly contact me here. So this is my email. It's Alan_Wang. So it's kind of overlapped with this highlight here. So this is my email. So for students interested, you can directly contact me. And also about the Baylor University, it's a Waco. It's about 3 hours drive from here. And the Baylor was just promoted to R1 last year. So basically we are becoming a R1 university, which means research intensive university. So a lot of efforts is being put on to conducting research with the PhD programs. Okay, there's a few more minutes. I just want to shift away from the technical part and go to my personal experience to provide some like a career guidance for PhD students in engineering. I understand the majority of you here are undergraduate students. So I want to share some personal experience so that you can seriously consider whether you want to pursue PhD for your future career. Let me see what happened there. So I want to make sure. Okay. So I want to emphasize my experience only applies to students in engineering and natural science, not including social science and medical science, which have zero background. So if you are interested in PhD in this program, my experience doesn't apply. And also, my experience only applies to PhD program. So if you are interested in master program, probably it doesn't work really well here either. And also, the students. This applies to students who have not started their professional career yet, or you just a few years in industry and want to come back to graduate PhD program. This experience doesn't apply to a mid-career, so who has been working in industry for 10 or 20 years in the mid-40s or 80s want to go to a PhD. They may seek a different advice as well. So but I believe it will be valuable to most of you here. So the first question is, why should I pursue a PhD program, a PhD degree? The answer is, unfortunately, nowadays, most research positions in industry and academia require a PhD degree. And even for the technology development program, most advanced programs also require a PhD. So this is just the reality here. So this trend. It's just like the tide lifts everything up. And also, if you take the PhD program, the 4 to 6 years of training will benefit your long-term career. So you will gain more skills, you learn more methods for scientific and engineering research, you have more in-depth thinking of the work you are doing, and you can build a more broad network for your future career. And also, working in the PhD program can motivate your interest in science and technology and release your hidden potentials. And many of you may not have research experience. You really don't know whether you have that kind of potential. But working toward your PhD program can potentially release your hidden potential, which you haven't realized yet. And also, right after your bachelor degree, you may not have really had a thorough plan for your future lifelong career. And staying in a PhD program will borrow you more time and make you more mature to plan your lifelong career. And also, if you get a PhD, generally you can get a higher salary and a better opportunity for promotion in your future career. And it doesn't mean every situation you will get this better, but generally you have a better opportunity for promotion and higher salary. And what kind of job you can get after your PhD? So most of the PhD still goes to industry. They will, absorb like 90% of the PhDs in the engineering area. So in the industry, you can take an R&D engineer in a high-tech company or big company. Like most of my students, they are now working in the high-tech company in Bay Area, like Cisco, Apple, ASML, Maximum IC. And here in Texas, there are plenty of job opportunity in Austin. It's called Silicon Hill rather than Silicon Valley. So there's a lot of high tech, and there are more companies moving from California to Texas. And in addition to the big company, you can also be a researcher in a national lab or government agency. So you can do research in the national lab or become an agent to manage the research in the funding agency like the National Science Foundation, Department of Defense. There are many program managers, but the minimum requirement is also a PhD. So if you don't have a PhD, how can you, working with other professors who are PhD and doing research? So that's a minimum requirement. And also you can be a technology leader or a founder of a startup company. So there are many programs to support the startup in the United States, like the Small Business Innovation Research. The government will give you the funding to develop some product, and then you can do the commercialization. And also, if you don't want to directly working as a technology, you can be a technology consultant. I believe this is a majority of the industrial job. There might be some other roles, but this will account for the majority of the industrial role. And in addition to industry, academia, it's a minority, but still it's a very attractive area to choose as your career. Especially if a faculty in a college or university. For faculty, you have two different tracks. One is the non-tenure track. You can be a lecturer, which only work on teaching, or a research faculty, which only work on research. But the other track is called the tenure track or the tenured faculty. So you need to do both teaching and research. Just like my position is a tenured faculty, so I need to do both teaching and research. For the teaching, I teach undergraduate and graduate level curriculum, and also for the research, I mentor PhD students to help them to get their PhD degree. And for this position, generally you have different levels, like assistant professor, which you have 6 years to work on in this track. After 6 years, you will be promoted to associate professor with a tenure. And then if you are doing good enough, after a few years, you can be promoted to full professor. And unfortunately, getting a faculty position in the college is also become more and more difficult. And many PhD didn't get the job right after they graduate. You have to consider a postdoc position for 2 or 3 years to bridge the gap, so you can work in a university as a postdoc and then gain more experience and will enhance your successful rate to secure a faculty position. Well, PhD degree seems to be good, but how can I earn the PhD degree? It's not easy. You probably have to spend 4 to 6 years in a program. But even spend 4 to 6 years there is not a guarantee. It doesn't mean you can automatically gain the PhD degree if you stay in the program for 4 to 6 years. It has to depend on your performance. So in order to do that, you need to pass all the graduate level courses. So each university, they have their graduate level curriculum requirements. You need to pass all of them with a minimum grade. Different universities may have different requirements. But most importantly, you need to spend a lot of time in research. I mean, a lot. So the requirement is, you need to, in order to pass those curriculum, you have to keep a good GPA. But for the research, usually there are some specific requirement. The first is the publication. So you need to publish your work in the journal article or present your work in a conference. And also there are exams. So you need to go through your qualified exam, prelim exam, and defense exam. So for qualified exam, it's primarily for curriculum. So basically you need to take an exam to cover your curriculum you have taken. And the prelim exam is like a halfway of your research, say check your progress. And the defense is the final one. So you just present all your work, the committee will evaluate your work and vote pass or non-pass of your PhD defense. And of course, you need to write and publish your PhD dissertation as well. So that's pretty much, my experience I would like to share with you, and I hope that can help you to understand a little bit better of the whether you want to consider the PhD program for your future career. And that's all my information here. And again, thank you for everyone's attention, and I would like to take some questions.
The first question students have is, what and how much are you paying your PhD students at Baylor?
It's a university standard. The university has a standard there. I think it's because of inflation, they are adjusting. I think right now it's probably $2,300 per month. But it's going to be increased this year. So that's probably, yeah.
All right. And we'll take 1 or 2 more questions, and then we'll have to go yes and that.
So you're mentioning the biosensing capabilities, and specifically diatoms, right?
Yeah.
Okay, so how do you detect things that don't produce in diatomic formats? Because obviously that doesn't cover every molecule. Do some things produce diatoms in other abundances, which makes it easier to detect a certain thing, or how does that work?
No, we don't tell the material we want to detect. Basically, we use a diatom as a general material, and then we put a nanoparticle on that. So for anything we put on, we rely on spectroscopy. We have a laser shining on the diatom material, and then it produces a spectroscopy. And then we detect the spectroscopy, and then we identify and differentiate different type of molecules. You're right, not everything can be detected. There are some things that are similar. You may not be able to detect it. For example, protein and DNA, they are difficult to detect because the chemical structure between DNA and proteins, different type of DNA protein are very subtle. It's just a slight arrangement. You can't really use diatom to detect such tiny stuff. So what you usually do is you do labeling, which I don't have time to discuss here. So basically, you label the DNA you want to detect with a certain type of dye, chemical dye, okay, which give you unique search signal. And then you do an immunoassay using antigen-antibody binding. So you bind it, and then you shine the light on the structure. It didn't give you the signal from the DNA or protein itself. It gives you from the chemical dye, search dye, you label the material. So this is called a label immunoassay. Yeah.
One more question. Anybody? Questions on
Is there a limit to the number of frequencies of light you can pass through
Diatom or?
yeah, the nano photonic substrate?
Yes. The answer is yes. For every substrate plasmonic or photonic, it's a resonator. It only works for a particular wavelength. So that's why we need to, design those materials or select different diatom species to work with the wavelengths you are interested.
Oh, okay.
It's a resonator. So if you think of resonator, it's frequency dependent. Yeah.
If you've got more questions, Dr. Wang will be up here. Otherwise, if you want to join us for lunch, we'll be in the Joyce Room on the corner cafe. And thank our speakers.
Thank you.
Stop the recording here.